All right, welcome back to Physics 210. At our last lecture, we talked about a few things from chapter 24. Chapter 24 was called Optical Instruments. And so we talked about the optics of the eye, including corrective lenses, how glasses work. We talked about angular magnification, which is going to come up again in a second. Angular magnification, capital M. So this is, related to how big an object looks when projected onto our retina. That is, the light-sensitive part of the eye. And we also talked about the magnification of a magnifying glass and how that works. That is, the angular magnification is equal to 25 centimeters over the focal length of the lens. 25 centimeters here is the near point of the eye, so that's the closest we can hold something and still focus on it. Okay, so today we are going to talk about microscopes. So this is our first real, optical instrument, a thing made of multiple lenses that we can use to accomplish a goal. So our simplest possible microscope consists of two lenses. The objective lens and the eyepiece lens. And we'll draw an optical axis here. So the kind of cartoon version, we'll draw a good ray diagram here in a second. The cartoon version looks like this. We have our object that the objective lens turns into an image. Let's draw this actually correctly. It gets turned into an image, and then the eyepiece the eyepiece lets us observe the image from close up. So the objective lens gives us an image over here. The eyepiece lens we use to observe this image, and it gives us an image of that image that is, an infinite distance away, focused really far away. Okay, so let's draw an actual ray diagram. With the magic of video editing, I think I will speed this part up a little bit so you don't have to sit through me drawing all the rays. Okay, so here's our ray diagram. We have our object positioned near the focal point of our objective lens, but just on the other side of it. This gives us a magnified real image on the right side. And this real image is located exactly at the focal point of our eyepiece lens. The result of which is our virtual image that we'll see with our eye is going to be seen a very large distance away, an infinite distance away, and is also going to be infinitely big. So the angle subtended by that object, we can see on here. I mean, if we imagine that our object, the virtual object we see is going to be, some big arrow that looks like this, right, where these rays are meeting up some really long distance away. The size of this object is going to be the same as this angle here. We will call this theta seen. That is the size of the object that is, seen by the observer. That is going to be the same angle as that. And assuming these are small angles, we can see that theta seen is going to be equal to the height of our image, which we call h prime, over this distance, which is the focal length of our eyepiece lens. So this is h prime over fi. We also know how big h prime is. So note that, from the objective lens information, we see that h prime, or we learned these equations before. I'm going to clear a little bit of room here. H prime is related to the ratio of the object and image distances. So that is h prime is equal to minus h times s prime over s. That is the image distance divided by the object distance times the actual size of the object. Okay. So we can plug this into there and get that theta seen is equal to minus h times s prime over s times fi. Okay, so s prime. Now we're going to make a couple approximations for typical values for a microscope. So s prime, the image distance, that is, in a real microscope, that is most of the distance between the two lenses. So in other words, this distance, fi, is much smaller than the distance between the two lenses. So s prime, which is this, we can approximate just as being the distance between these two lenses. So that length is given a name for microscopes. That is called the tube length, which I will label on here. And that is abbreviated capital L. Our object distance, S in this, is, this distance on the diagram. Now, because we place the object close to this focal point, that, this distance is going to be approximately the same as this distance, so we can write this distance S as being approximately equal to the focal length of our objective lens. So this is going to be equal to minus h times s prime, which again we're calling L, over s, which we're saying is approximately equal to f objective, times fi. Okay, I'm going to make a little room, dealing with a small whiteboard today and for the foreseeable future. We're going to make a little room over here. Okay, so without the microscope, the best we can do, the biggest we can see this object, is holding it up to our eye right at the near point. So that is as close as we can focus with our eye. And we saw that the near point is approximately 25 centimeters away for normal eyes, which means the biggest, the biggest our object can look without the microscope, we will call theta, maybe we'll call it theta bare eye or something like that. The book doesn't have a good name for this variable. So theta seen with the bare eye is going to be just, the size of our object and the distance it is away. That is the near point distance, and that is, that is what we see. So this angle is just going to be equal to h over this near point distance, which is h over 25 centimeters. So the angular magnification then is the ratio between these. It is, how much bigger it looks through the microscope versus how big it looks without the microscope. So we can divide these two. I'm going to sadly erase our microscope here so we can do this division. And we get the following. Our magnification is equal to theta seen over theta bare eye. So that is equal to minus HL over our two focal lengths divided by h over 25 centimeters. And now something good happens. Our h's cancel, which is good because, our magnification is a property of the microscope, so the size of our object shouldn't depend on, the power of our microscope shouldn't depend on how big the thing is we're looking at. So those h's cancel, this 25 centimeters ends up in the top, and we get minus 25 centimeters times L over the two focal lengths of our lenses. So this is the magnification of a microscope with tube length L and those lens focal lengths. I'm going to rewrite this slightly for reasons you will see in a second. So we will rewrite this, just rearranging these variables as minus L over the objective focal length times 25 centimeters over the eyepiece focal length. So this is just rearranging this in terms of algebra. And now our magnification, we can kind of see, is made of two different pieces, right? This one on the left, minus L over the focal length of the objective lens, this is actually just our lateral magnification, lowercase m, that we learned before, for the objective lens side of the system. So we start with an image of size h, and we end up with an image of size h prime that equals h times this. So this tells us how big the image is that we get. This, 25 centimeters over the focal length of the eyepiece lens, this should also look familiar. This is exactly our angular magnification for a magnifying glass. And that is because what's going on here is our eyepiece lens is letting us, look at this, the image we got from the objective, just as if we were holding a magnifying glass close to something and looking at it. So the product of these, the magnification from the objective lens and the magnification from the eyepiece lens, is our total angular magnification for the microscope. So we can think of these two lenses as each doing their own thing and multiplying together. All right, I'll leave that up for a moment. So in an actual microscope, let's draw a little cartoon of an actual microscope. So a microscope we might use in the lab, one type of microscope we might use in the lab looks kind of like this. And I'll explain the parts here in just a moment. So maybe it looks something like this, I don't know. Different microscopes look different things. Okay, so what we have here is a eyepiece lens. In the upper right, this is, the thing we actually look into. And down here are our objective lenses. In fact, there are, the way I've drawn this has a few objective lenses. And this is kind of bent at an angle just so you can have your head at a nice relaxed position relative to your sample. So somewhere in here there is, something like a little mirror. It actually uses a prism, but for our purposes we can kind of imagine it as being some little mirror so that our view, is reflected down through this objective lens that is vertical. The reason we have multiple objective lenses is this whole piece on the bottom can rotate. This is called the turret, or the objective turret. So this piece rotates and we can pick which of several different objective lenses we want to use to look at our object. So our object sits on a stage here. And so our objective lens is fixed in place other than this rotation. It cannot move up and down. This whole part of the microscope is rigidly connected together. So the way we bring our object to the right position is actually by raising this whole stage up and down. So this whole thing moves up and down with, sometimes there's a big focus knob here or here. So as we saw in our ray diagram, if we're not moving the eyepiece lens and we're not moving the objective lens, there is only one position on a ray diagram that gives us a nice focused image, and that is this place that we picked just to the left of the focal point of the objective. So there is some place in space relative to this lens right here, maybe, that is the only place where we have our object in focus. So the purpose of this stage is we can move the object up so that it is right at this position, and when our thing is at the right height, then we get a nice image through the eyepiece lens. So this is, a typical laboratory microscope. Of course, real microscopes are going to have, eyepiece lenses and objective lenses that are not just simple thin lenses. They might each themselves be combinations of 2 or 5 different actual glass lenses, each of them doing a slightly different thing, but working in combination to give us something like the thin lens model that we saw. Lastly, and I left this equation up here for a reason, our magnification depends on the objective magnification and the eyepiece magnification. And when you use a actual microscope, this is important. Often your eyepiece lens is labeled with a magnification on it. Often it is 10x. There are other ones available. I think 10x is the most common. And each of your objective lenses also has a magnification labeled on it. Maybe this is a 40x and this one is a 100x, etc. You can, on some microscopes, you can swap them out, unscrew them, and put different ones on. So the total magnification you get from the whole instrument is the product of these two. So if you have your 40x objective lined up, under your microscope lined up with your object, that means the total magnification you get is the product of these, right? So you have a 10x eyepiece and a 40x objective. That gives you a total magnification of 400x when those are the two you were using. All right, well, I think that's all I have to say about microscopes. Thanks.